Welcome to Podcast 2, Average Rate of Change. So average velocity, and this is in your notes, let S equal S of t be the position function. Lots of times we call S the position function. Just is. Where S is position in meters and t is the time in seconds. So if we want to find the average velocity, your average velocity is going to be your change in displacement, or change in position, divided by your change in time. If this isn't in your notes, add it to your notes, right? Because that's how we're going to calculate out average velocity, and that's what you did in those problems dealing with Wile E. Coyote. You figured out his change in displacement, his change in position. Displacement is change in position, and then you divided by that by how much time had elapsed. The change in time. So average velocity over the interval t1, t2 is given by, right, so it's the slope of the secant line, it's the change in position over change in time, and you need 2 points. Right? So it's whatever you're finding the change in your average velocity between. So if I'm finding it between 1 second and 3 seconds, then it's going to be S of 3 minus S of 1 divided by 3 minus 1. Right? So it's going to be your average velocity is your change in position over change in time. So I think this problem's in your notes. A rock is launched vertically upward. The height of the rock is given by S of t equals 100t minus 10t squared. This is how we find this is the position of the rock. If we want to know the position at 1 second, we plug in 1 for t. If we want to know the position at 10 seconds, we plug in 10 for t, and so forth. We want to find the average velocity over the time interval 1, 2. So we know what our change in time is. We have our time values. We need our position values. So to find that, we simply plug in 1 into S of t, and we get 90 meters. We plug in 2 into S of t, and we get 160. I didn't bother to go over this step by step because I didn't think plugging in and simplifying would be too effortful for you. All right, and so now we need to take the change in time over the change in position divided by the change in time. Right? So I have it listed above here, change in time and change in position. I tend to just write it like this and not calculate it out separately. Average velocity, okay, would be f of 2, or I should say S of 2, sorry. S of 2 minus S of 1 divided by 2 minus 1. I find that easier because what if instead of subtracting S of 1 from S of 2, I reversed it. I kind of like to see that, yes, I've matched up the points correctly. Let's get rid of this thing. All right, so our average velocity, S of 2 was 160. S of 1 is 90. And of course 2 minus 1, which would give us 70 divided by 1, or, oops, that's a 1. Or 70 meters per second. Make sure you include units here, right? So if our position is in meters and our time is in seconds, our average velocity is going to be in meters per second, right? I think this is the easiest way to write that down. And this is what I would want to see. You don't necessarily have to write in you plugging it into the equation. All right, so now we have a table, right? So this is a very useful problem for us to go over. I'm hoping that this problem is in your notes. If this problem is not in your notes, you're going to want to jot this one down. I don't have the notes in front of me because I gave them all to you. So we have a student throws a book in the air and records the book's height as a function of time. We want to find the velocity of the book between half a second and 2.5 seconds. What does the sign of your answer tell you about the book? Now this is actually super easy. I can only ask you the average velocity for times that you actually know. So I couldn't say, I've got 0, I've got half a second, but you might have trouble with a quarter second, right? We can approximate it, and we'll look at that much, much later. But I can ask you the average velocity between a half a second and 2.5 seconds. So you should be able to take a table of values and find your average velocity as well. Okay? So it's going to be the change in the height divided by the change in time. And I want to make sure that, when I set this up, that I match up my variables. Right? So I'm going to take S of 2.5. I'll do the larger time value. S of 2.5 minus S of 0.5 divided by, I even said 0.5. Divided by 2.5 minus 0.5. That's our change in time. All right, so S of 2.5, that's 118.5. S of 0.5 is 44.5. Right, so notice that those Y values or height values match the time values. So this is 2.5 minus 0.5. And then we just simplify. Right, so 118.5 minus 44.5 is going to be 74, right? Yes, I think so. And then 2.5 minus 0.5 is just going to be 2. So this is going to be 37, what's the units, or feet per second. All right, so that's the first question. Find the average velocity. There it is, 37 feet per second. That's how fast it was traveling. That doesn't tell us how fast it was traveling at 2.5 seconds or 0.5 seconds or necessarily any value in between, but the average was 37 feet per second. All right, and we'll talk about later on, well, does that mean that at one time it was 37 feet per second? We'll talk about that later. But for now, I should be able to find average velocity and the sign. Right, so notice that the sign is positive. What direction was our book going? The book is going up. Right, she threw the book up. Right, so velocity is directional. If I have a positive, I'm going up or to the right, and depending on what we're talking about. And if it's negative, it's going down or to the left. So this was positive, book's still going up. All right, at some point, it's going to switch and start going down. And we can actually see that the position values are getting lower after 2.5 seconds. All right, so you should be able to find average velocity from a table of values. That wasn't hard, was it? No, that was easy. So geometrically, the average rate of change of f over x1, x2 is the slope of the line through points P, x1, f of x1, and Q, x2, f of x2. Such a line is called a secant line, right? So you should know what a secant line is. A secant is a line connecting any 2 points on a curve. We also call this, there's another name for it, average rate of change, or the difference quotient, right? So we have three ways here to name this. Over the interval AB. We call it the difference quotient because it's the quotient of the differences. The differences between the value of the function over the differences in the x values. Right? So a line through 2 points on a graph through P and Q is called a secant line of the graph, right? And we can find the slope of that. I don't know why there's a random slope of here. I have a feeling that it went with something else I already erased. Right, so you should know that the average rate of change, the difference quotient over an interval, and the secant line is all talking about the same thing. Okay? So a secant to the graph y equals f of x, its slope is just change in y over change in x, just like you'd find the slope of any other line. And it happens to be the average rate of change of f over that interval. So now the closer the 2 points are together, the closer the estimate. Right? So if my points are very, very far away, right, it may not necessarily approximate my curve very well. Right? So if we look at those 2 points that I have up there in my picture, now those 2 points aren't very close together. It's approximating the slope of that curve there, but at different places, the slope of the line and the slope of the curve are certainly different. But notice what happens is they get closer and closer. Right? So the closer this line gets, that secant line gets to my curve, notice it's really very well following that curve there. So the slope of the secant line can be used to estimate the slope of the function. They're not the same, but we can use that to estimate it. And the closer those points are, right, the better our estimate is. As I star things, you can kind of know, just double check. Is that in your notes? If that's not in your notes, that's probably a good thing to write down. Right, so to define tangency for general curves, and I think I put this whole picture in there, we need an approach that takes into account the behavior of the secants through point P and nearby points Q as Q moves toward P along the curve. Right? So first of all, we're starting with something we can calculate, like the slope of a secant line. That's easy, right? You've been doing that since Algebra 1. All right, so here we have an example. We have P and Q, right? And we can find the slope of that line. But what if we start moving that point Q and we move it closer and closer? So second, investigate the limiting value of the secant slope as x approaches P along the curve. If the limit exists, we're going to take it to be the slope of the curve at P and define the tangent to the curve at P to be the line through P with this slope. Now, maybe that's a mouthful for you right now, and you're like scratching your head. I'm not 100% sure what Ms. Mashadian means. But we're going to go through it step by step, and then you will be. So in essence, notice where if Q is far away from P, my 2 points are far away from one another, well, that may not be the best approximation of the slope of that curve. But if I start pushing Q, if I start pushing it closer and closer and closer, closer and closer, follow the line here, and closer, the closer this gets, notice the better that slope of that secant line approximates the slope of our actual function. And that's what we're going to be looking at. I see the word limit, the limiting value. What do you think we're going to do? If you say, take a limit, you're correct. So we're going to look at the difference between now instantaneous rate of change and average rate of change. Instantaneous rate of change is the limit of that difference quotient. So if I take away the word limit, I was going to cover it up. Like you can see if I cover it up. All you can see is the computer screen. So if I take this away, this is the difference quotient. It's just average velocity. It's the slope of the secant line. Oops. I'm missing a C in there. Slope of the secant line. So if I take away the word limit, that's all that is. Right? This is without the limit. If I add the words limit in there, and then h here wouldn't be going to 0, that would just be f of a, it would just be a plus h minus a. It would be the difference between those values. So actually it would be h. But if I put the word limit in there, well now that's no longer just a difference quotient, average velocity, slope of the secant line, average rate of change, it becomes our instantaneous rate of change. So the average, and this should be in your notes, I'm sure it is, but let's do that. You double check. I'm starring things that are really important. There are other things that are really important, but I want to make sure you're making sure that this is in your notes. So average rate of change is, or AROC, or ARC, is the slope of the secant line between 2 points. Sometimes that gets abbreviated ARC, and sometimes it gets abbreviated AROC. The instantaneous rate of change, or IROC as it's sometimes also abbreviated, is the limit as h goes to 0 of the slopes of the secant line. It is the slope of the tangent line. Okay? So very, very important. The average rate of change is the slope of the secant line between 2 points. As that second point gets closer and closer and closer, so that the difference between the 2 points goes to 0, we don't have a secant line anymore. We have a tangent line. Remember, a tangent line only intersects at 1 point. And that's our instantaneous rate of change. We're not looking at the rate of change between 2 points in time. We're looking at the rate of change at exactly 1 point in time. That's what instantaneous rate of change is. Note that the instantaneous rate of change is the same as the slope of the tangent line at point P. Okay? Similarly, the average velocity approaches the instantaneous velocity. So as the limit, as the difference between the 2 points, the A plus H and the A, as that goes to 0, right, then there's no difference in my point. And we're not looking at average, we're looking at instantaneous. So average rate, I got a star there already. Average rate of change is a secant line between 2 points on the curve. As the distance between points approaches 0, we have the tangent line, and the slope of the tangent line is the instantaneous rate of change. That is a key point. It's the biggest point in this lesson I've made. Key point. It's the big idea in my lesson here. All right, so consider the following position function. S of t equals t squared minus 4t. And we're going to find the instantaneous velocity at t equals 3 seconds. And this, I believe, is in your notes. All right, so that means to find that instantaneous velocity is the same as instantaneous rate of change, because velocity is a rate of change in speed. All right, so we're going to take the limit as h goes to 0. All right, and now I need to replace s here with what s is, which is this. So s of a plus h needs to get replaced with the t squared minus 4t. And I'm going to plug this. This is going to be my one x value, and this will be my other x value. Right? And we have to plug that in to our function. Right? I'm just going to do it right here as we're calculating out the limit. All right, so we have, I'm plugging in the a plus h here into t squared. So that's a plus h squared minus 4a plus h. Right? Everyone sees that we just plugged that into the function. Okay. Minus, and I like to use parentheses because then you don't worry about forgetting to distribute. Now I got to plug a in. Right? So that would be a squared minus 4a. Oh, excuse me. I'm going to leave it as t's, not a's. I'm sorry, our variable is t. My equation here is written as with an a in it, but we're using t's. So I'm sorry, t plus h squared and t plus h minus t squared minus 4t. I like to keep it in terms of time. All divided by h. Right? Whether it was a t or an a doesn't really make a difference. It's just that we have t as my variable in that equation. All right, so now we need to simplify. We have the limit as h goes to 0 of t plus h squared. If you don't mind, I'm just going to square it in my head and write it down. So that would be t squared plus 2th plus h squared. Everybody okay with that? If not, pause the tape, multiply t plus h times t plus h, and you'll see, yeah, it's that. Right, we have two th's because we multiplied the outer and the inner products, right? Minus, so I distribute that 4, minus 4t minus 4h minus t squared and then plus 4t, right? Because I distributed the negative, right? So I always use parentheses so I don't forget. Now you might think, oh my gosh, this looks so complicated. It's not. I've done some simple algebra, and look at that. I have some terms that are opposite one another. So this limit as h goes to 0. Notice I have t squared minus t squared. Goodbye, t squared. I've got a 2th, and there's no other th's. So we have 2th. I have h squared. There's no other h squareds. Negative 4t and a positive 4t, that's gone. And then we have the negative 4h. So it's not a bad idea to do this when you see that you have opposites so that you don't write them down. So those were opposites, and then these were opposites. So they just canceled out. So now I'm left with this. Now, I don't think I have to actually do the plugging in for you to realize this is going to be indeterminate, right? Because if I multiply 2th, I plug in 0, that's going to be 0. 0 squared is 0. Minus 4 times 0, I got 0 in the numerator. When I plug in 0 for h, I got 0 in the denominator. But hopefully you see that there's something we can cancel, we can factor out of each of these terms, and that's an h. So it's the limit as h goes to 0. We'll pull out the h there, get the h out of there, and we got a 2t. And we have another h. And we have minus 4 divided by h. Now we can cancel these two out. And now it won't be indeterminate no more. Now we can plug in. So we have the limit as h goes to 0 of 2t plus h minus 4. I'm going to plug in 0 for h, and I have 2t minus 0, or plus 0 minus 4, which is 2t minus 4. You're not necessarily going to get numeric answers, strictly numeric answers. You might get you may have a variable still in here, and we'll talk about why later. But this right here, that right there is my instantaneous rate of change. Right? And if I want to find out what it is for 3 seconds, what do you think I have to do? I have to plug in. So this function here is that 2t minus 4 is the function that gives me the instantaneous rate of change for any time. If I want to find it at 3 seconds, all I have to do is plug in 3 for t, and we've got it. So our instantaneous rate of change at 3 seconds, I'm just going to put IRC 3, is 2 times 3 minus 4, so that would be 2, and what was the units of measure here? Seconds, let's just say meters. 2 meters per second, because it doesn't list position. Right, so that 2 meters per second is our instantaneous rate of change at 3 seconds. Okay? It's going to be different for at 4 seconds and 5 seconds and so forth. Right? But once we have our function to calculate out our instantaneous rate of change, all we have to do is plug that in, and we can find our instantaneous rate of change. Okay, so this is, over here we had key point number 1, and over here we have another key point. How do we find the instantaneous rate of change? And essentially it's just kind of carrying on my key point number 1, isn't it? Right, so I think this is a good place for me to stop for a moment and start the next podcast. I think I can do one more because we're only at 27 minutes for podcasts. But I don't like these to get too long, so I'm going to stop this one, and then let's look at this problem over here. All right, see you next podcast.